In this second section of our OER statistics course, where we are investigating the chi-square distribution, we will discuss one of the three chi-square tests, and specifically the goodness of fit test. In these types of hypothesis tests, you determine whether the data fit a certain distribution. Usually, your data are categorical data in more than two categories, and you are trying to see if it fits a certain distribution. It could be a binomial distribution, it could be a uniform distribution, and we will use a chi-square test, meaning the distribution for the hypothesis test will be chi-squared to determine if there is a fit or not. Your null and alternative hypothesis for this test may be written in sentences or may be stated as equations or inequalities. And I will demonstrate in one of the examples. We will also see it in Art of Stat, how Art of Stat will state it with mathematical expressions, even though most of the times we will just write it out in a sentence. For the goodness of fit test, if you remember, your test statistic will be a chi-squared score, and that is the sum of z-scores. And assuming that you have k categories, then you will add over all k categories these z-scores, and the z-scores equal the observed data value, the one you collected from your sample, minus the expected data value squared divided by the expected data value. And these particular terms of the test statistic, observed minus expected squared divided by expected, is called the Pearson residual. And the sum of those k Pearson residuals over the k categories will equal to your chi-squared test statistic. The degrees of freedom for this chi-squared distribution based on the null hypothesis will equal to k minus 1, which again, k is the number of categories. The goodness of fit test is almost always right-tailed because the chi-squared test statistic is positive, and if the observed values and the corresponding expected values are not close to each other, then these Pearson residuals will be very large, resulting in a test statistic that is very high out of the right tail of the curve, and that's why right-tailed is usually what it's going to be for our alternative hypothesis. The expected value, not for the alternative hypothesis, but for the test that we will conduct, because the chi-squared will be the sum of those differences. The expected value for each cell needs to be at least 5 for us to use the test. So if you have categories that have an expected value of less than 5, then you will have to combine categories so that you are able to conduct the chi-squared test. So let's do an example. Absenteeism of college students from math classes is a major concern to math instructors because missing class appears to increase the drop rate. Suppose that a study was done to determine if the actual student absenteeism rate follows faculty perception. The faculty expected that a group of 100 students would miss class according to the following table. The table indicates that the faculty expects that 50 students will miss 0 to 2 classes per term. 30 students will miss 3 to 5 classes per term. 12 students will miss 6 to 8 classes per term. 6 students will miss 9 to 11 classes per term, and 2 students will miss 12 or more classes per term. And this is out of 100 students. So you can also have expected probabilities. So these are the counts. That's a total of 100. But the probability, the proportion, or probability of each one expected would be 50%, 30%, 12%, 6%, and 2%. A random survey across all mathematics courses was done to determine the actual number of absences in a course. So the actual numbers will be the observed numbers. And we didn't have 100 students this time, or did we? 60, yep, we did have 100 students again. So we observed 100 students, and we ended up with 35 students missing 0 to 2 classes, 40 students missing 3 to 5 classes, 20 students missing 6 to 8 classes, 1 student missing 9 to 11 classes, and 4 students missing 12 or more classes. The question is, if we can determine the null and alternative hypothesis needed to conduct the goodness of fit test, the degrees of freedom, and can the information in the charts be used to conduct the goodness of fit test? So the first part is that we will want to do is whether we can conduct a goodness of fit test. If we can, then we can state the null and alternative hypothesis. And the answer to this is that actually we cannot. And the reason we cannot conduct a goodness of fit test is that according to this note here, we are supposed to have expected value for every category, at least 5. And here we have an expected value in this category of 12 plus of 2. This 2 is less than 5. So actually we cannot conduct a goodness of fit test the way this is. So what we will do for that is we will actually combine these two categories. They are neighboring to one category called 9 plus. And this 9 plus category will have a total of expected of 8, and 8 is greater than 5. So this 8 that is greater than 5 will now allow us to conduct a goodness of fit test with 4 categories. The categories will be absences from 0 to 2, from 3 to 5, from 6 to 8, and 9 plus, with expected values of 50, 30, 12, and 8. And then in that case, we will be able to conduct a goodness of fit test. So here we have to combine categories. We want to have expected counts that are greater than 5. Therefore, now we will have 4 categories. And we will have a chi-square distribution with degrees of freedom equal to k minus 1, which will be 3. And now that we can conduct a goodness of fit test, we want to state the null and alternative hypothesis. The null hypothesis is the assumption that the sample data will actually fit the theoretical distribution. So the null hypothesis will always be that the data will fit a certain distribution, and the distribution is the theoretical distribution for the null hypothesis, and that will be the teacher's distribution. So here my null hypothesis will be that absenteeism follows the faculty's theoretical distribution. And mathematically that will be that the probability of 0 to 2 absences will be 50%, that the probability of 3 to 5 absences will be 30%, that the probability of 6 to 8 absences will be 12%, and that the probability of 9 plus absences will be 8%. So in words, we will say that the null hypothesis that the absenteeism in math class follows the faculty's distribution or perception, and mathematically we can write this as equations pertaining to the proportions of each category in the theoretical distribution. The alternative hypothesis will be the negation of that absenteeism does not fit the faculty's distribution. Now notice that we are not going to say that the probabilities are greater or less than. We are going to say that the observed probabilities will be much more different than the expected probabilities. And that is because since all the probabilities must add to 100% or 1, if one of them is much larger, the others must be much smaller, so that we can always have a sum of 1. Now, however, because the test statistic chi-squared score will actually be the sum of the squares of the differences from the expected ones, even if the differences are negative or positive, when we square them, they will become positive anyways. So the chi-square test statistic will be a positive quantity regardless of whether the proportions that are observed are lower or higher. So our alternative hypothesis doesn't state any direction for each individual proportion. It just says that they will not fit this particular distribution that we said theoretically our null hypothesis will follow. We are ready to conduct the test. So in the next video for this section, we will actually be covering the full tests for these kind of hypothesis tests.